All right, let us get started. Okay, so the Project 1 spec is out. The Project 1 files are out in two versions, one for the new horn system and one for just plain Bison versus Flex. All of those systems should have online documentation. Let me know of problems. So you can choose to copy either of the two alternative Project 1 files. Just use one, don't use both, and carry on from there. You should all now be in teams. If someone isn't in a team, then you have not been following directions because you have not posted your teamlessness properly so that I could see it. And the Homework 3 autograder is running. I guess that's everything. Questions, administrative or otherwise? Issues? Problems? Okay, good. Little announcement. We have a job opportunity for those of you who are into web development. So anyway, you can get all of this. You can get all of this and learn what Moodle is, in case you don't know, by clicking, well, by Googling Moodle, yes, okay. Before we go there, however, let's go back to our somewhat problematic last lecture, or our lecture beset by technical difficulties, and just finish that up. So here was the business. We defined first and follow. This is the problem being solved by this. The reason that we even talk about these things is this first and follow stuff and all this math-looking stuff. Is that it's just a general technique for deciding which of several possible productions to use when writing one of these top-down compilers, or one of these top-down parsers, or recursive descent parsers. So the idea is simply that you choose when given a choice, like you're asked to parse an S, you choose the branch, the option, based on the symbols that can begin each of the right-hand sides, each of the choices. That's the purpose of first. And first also can also return a result saying, hey, this thing can produce the empty string. So before you choose the branch that produces the empty string, you'd better check to make sure it would be good in order to detect errors, to check that the next symbol is something that can follow, let's say, an S or a T. So that was the idea behind these sorts of things. That's how they're used. And if we look at a grammar like this, for example, the issue here is, well, what is the issue? First of all, here's a grammar. It actually turns out that this grammar is fine for doing top-down parsing. And what is the difficulty with it? It's a fine. It recognizes these expressions with slashes and stars, but there's a slight problem with it from the standpoint of writing not just a recognizer, but a complete parser. And what would that problem be?
Deciding which key to use.
No. That actually, it turns out that if we compute first and follow, it will turn out that that's unambiguous. There's another problem, small problem. Think about an expression and how this grammar is going to match it. So in particular, consider the expression A divided by B divided by C. How is this grammar going to match that expression? It will match it, and it will recognize it. But how is it going to do that? Yeah. Yes, so in other words, the only way you can match that is for this T right here to match the first identifier, and for the ET to match the second and third identifiers. So if A/B/C, the T would match A, and the ET would match B/C. Well, that's not natural. That's not the way you group these things. So you're going to have. So that means that in the actions, you're going to have to do some tap dancing to rearrange things from the way that the grammar gives them to you naturally. So that could be a problem. On the other hand, so that's a problem. But on the other hand, first and follow are pretty straightforward. Here's the calculation. I think I got it right. So P's, E's, and T's can all start with I, and there's nothing else they can start with. That's kind of obvious. ET, on the other hand, can start with ET can start with slash and star, but it also can produce empty, so we throw that into the mix. So if we look at this, we'll see, okay, so we have a choice we'll have a choice at some point between rules 2, 3, and 4. So the slash E always starts with slash, that's fine. Star E always starts with star, that's fine. And if ET produces empty, then the symbol that follows ET, follow of ET, which is right down here, is equal to the things that follow E, and that consists, for this grammar, that consists only of the end of file symbol. So the three choices here, the three choices for ET, end of file, slash, and star are all distinct from each other. Therefore, there's no ambiguity. Ambiguity is not quite the right word, but there's no difficulty in choosing a branch to take at each point. So this is from the point of view of writing a recursive descent, or what we call an LL1, a top-down predictive parser, this is a perfectly good grammar. It's just this little problem with the actions are going to have to do some extra legwork to get things associated correctly. This is a problem that we'll see we don't have with the tools that we'll be using. Now, but we can deal with this problem by cheating, which is always fair game in computer science, as long as it doesn't involve copying somebody's work and misrepresenting it as your own. If it instead involves being impure, well, impurity is the name of the game. We can do this by simply making the observation that, well, look at this. This grammar, all the grammar is trying to say is that we have a list of these T things separated by slashes and stars. That's all it's trying to say. So why don't we just make use of that? So what we'll do is, first of all, we'll start off. If we're computing, let's say we're having this grammar build something for us, so it's returning a tree or what have you. The first thing we'll do is to compute an E as well. Let's go back and look at this. To compute an E, we need a T followed by an ET. Okay, so that's simple. We'll start with the T. And then to do the ET, well, we're going to continue doing something until we get to some condition. What do you suppose is going to stop this loop? So when should you stop trying to build a tree at this point, based on this grammar here? What's going to stop us? Yeah. That's right. So what we can do is, as long as we're seeing slashes and stars, we're not seeing end of files, we can continue. We know that there's more to collect. So at this point, we're going to we're going to have a choice. At this point, we have a choice between two things, slash and star, so we can choose either one of them. So if it's a slash, then we scan past it. We get the next t, and we group those two together. We group the t that we've got so far and the next t together to make a running sum here. And otherwise, we'll scan past the star, and we'll group that with the preceding stuff to make a multiplication. Now, and then when we're done, we're going to return as the semantic value. We're going to return. Easy question. That's why you're not getting it. Easy question. Yes. Go ahead. R. Yes, we're just going to return R. Okay. So with this technique, you throw in this technique, and you can basically make this work, which is kind of nice. On the other hand, there is this problem that on the other hand, you can also have tools. If you think back now at the recursive descent compiler that we've been building or that we've been looking at, there's a very obvious translation from grammar to program. It's every time you see a non-terminal system, call the corresponding subroutine, corresponding function. Every time you see a terminal symbol, scan past it. Every time you have a choice, use the first and follow sets to discover what to do. So that means that we can actually make this into a table-driven compiler. If you do that, then of course you don't have this, you can't just handcraft these while loops and you have to redo your grammar, but that's, many people find that that's not so much of a problem. Personally, I prefer not to have to worry about it, which is why I use bottom-up parsers instead. But it's really not particularly difficult to use this. So this is top-down recursive descent compiling, and as I say, this can be automated. It can be table-driven, or you can automatically convert into recursive descent compilers. And it's really a very nice technique especially for small languages. A pretty nice technique, as long as you don't mind the fact that the grammars occasionally require some hacking to make them fit into the appropriate mold. Okay, so I think with that we can finish with top-down stuff. Just some words of advice. For some reason, people often get hung up on this first and follow business. Now, just for your information, the tests that we give you in this class are, of course, of limited duration. Clue, right? Clue. This means that we can't very well ask you to do extensive computations of first and follow sets on the test. That would not be reasonable. Not that we're incapable of being unreasonable, but you know, it really affects the HKN ratings when you're unreasonable. So it might occur to you that it's probably the most efficient use of your time to just understand what these things mean. So to the extent that with a simple grammar you can just sort of eyeball the grammar and figure out what the answer to the question is if it involves first and follow, rather than having to do this calculation. And I think you'll find that if you internalize just exactly what these things are talking about, you might have an easier time understanding what they're for and how to use them and how to compute them, for that matter. So just a hint, right? Don't get hung up on these things, because even though it seems to be, it's a common problem to get hung up on first and follow, but it shouldn't be, because they should be really intuitive. If they aren't intuitive, then you know what to study. Okay, or what to ask us or the TAs about. Okay. Somebody asked me on the news group, by the way, an interesting question. They said, we only see context-free grammars. What's a non-context-free grammar? So I posted one. Warning, just in case anyone sees it and panics, please let me reassure you, we're not going to look at non-context-free grammars in this course. They are an advanced, they've been used to define one programming language, and that was Algol 68. And from the name Algol 68, you might guess that they haven't been used in the intervening 33 years, and that's, or 43 years. Yeah, 43 years. They haven't been used in the intervening, good God, I'm getting old. They haven't been used in the intervening 43 years, and it's for a good reason. So look at the answer that I posted and be amused by it. Maybe even try to understand it if you feel like it, but please do not panic as a result of seeing it. I'm not saying it won't be on the test because I never say that, but you be the judge. Okay, did I see a question? No, okay. Why don't we just back out of here and proceed finally to the topic we were supposed to do last time. We were supposed to get to last time. Now, so far I've shown you this technique for parsing grammars, and what I've said basically is sometimes it works, sometimes it doesn't. And so sometimes it doesn't work for good reasons, like you've written a nonsensical specification. Sometimes it doesn't work just because of the limitations of the parsing method. So if you write a grammar such as E goes to E plus T, recursive descent can't handle it, even though it's a perfectly good grammar. So I'm going to take a little time out here and look at how we can do this in general, because it's kind of interesting. There's a little bit of interesting history here, and it also has some potential tie-ins to parallel processing. All right, so first of all, it's the boring slide. It's just there mostly for you to refer to when you're trying to understand the other slides. So from now on, my non-terminals will be capital letters. This is unfortunately the opposite of the convention I use in the Horn system, but never mind. And I'll use lowercase letters for terminals. And then I'll use Greek letters for just right-hand sides, strings of bunches of symbols. And like that, like alpha equals this. So in other words, I might have a right-hand side that has n symbols, alpha 1 through alpha n. I'll just refer to that as the whole thing as alpha. So here are some examples. A alpha that's the form of this production over here. And here is a derivation. I will B goes to some string that looks like that, so it goes to a bunch of symbols that has an A in the middle of it, and then that goes to this. That means that that's just a way of writing that we've transferred. We've taken one step in the derivation to get me this first string, and then we've changed the A to something else to get the second string. That's all it means. So it's just notation. Unfortunately, I didn't find an application here for the Hebrew alphabet, but I'll work on it. It will happen sometime. It's not really very traditional for this sort of thing. So here is the problem. First, there are these problems with recursive descent compilers that we've talked about. So first of all, it doesn't handle left recursion. That is, it doesn't handle something that looks like a recursive function with the recursive call as the first item. And so the question, what I'd like to do is come up with a general technique that will work, that sort of has the same flavor as recursive descent, but will always work. So first of all, we start with here's a general thing for doing that basically summarizes what we've been doing with recursive descent. So to parse something, we choose some production, any production, right? And then that production will have the general form of a context-free production, namely a non-terminal symbol A goes to some bunch of symbols. All right? Now we'll see if using that production works. So we'll look to see whether the first symbol, so we'll look at the symbols in the production, and So we'll look at the symbols in the production. If a symbol from that right-hand side happens to be a terminal symbol, then what we're supposed to do is scan it. Namely, we'll check to see whether that terminal symbol is equal to the next symbol of the input. And if it is, we'll advance the input. So K will be the pointer into the input here. If the symbol is a terminal symbol but it doesn't match the input, then that's an error, that production isn't going to work. It doesn't match, so we give up. And otherwise, we continue parsing. This time we'll parse with, but this time we'll parse with the rest of that right-hand side. So we've gotten past alpha 1, and we'll just parse alpha 2 and so forth. So that's basically how we're going to do that. And the next thing that we're going to do is, the problem with this grammar, however, is that, basically what we're going to do is we're going to take that string, we're going to take the rest of the string, and we're going to try to parse it according to the non-terminal symbol for x. And then we're going to do that for each of the symbols in alpha. So this is basically an algorithm, a procedure that describes exactly what I said we would do in a recursive descent compiler, except I have written it out like this. And I also have this business about giving up, which is something of a problem. Now, so the idea about this is that when the grammar succeeds, it's going to return the position in the input past what it's just scanned. So it's going to parse the string s it's going to try to match non-terminal symbol a to the string s, and it's going to return to us the amount of s, the number of characters in s that it has successfully matched. That's the way it's going to work. And occasionally it will fail. Occasionally it will just give up, and sometimes it will succeed. So, we're going to interpret this program a little differently from the way we normally interpret programs, which means specifically we'll say that if there is a way that this program can work, in other words, if some of the choices that we make of productions up here, if there is some choice of productions up here that works, that gets us all the way through the string without giving up, then we'll say that we accept the grammar. We accept the string s, or s matches a. Otherwise, it doesn't. Right? So that's the idea. We'll choose these productions non-deterministically, and if there's any way we could succeed, we'll say that we have succeeded in parsing this thing. So it's just like an NFA, except there's a lot more than just what state are you in to keep track of. Now, this is not a normal programming language feature. Normally, your program comes along, it chooses something, and it either works, and if it doesn't work, the whole program crashes, and that's the end of it. Okay. But in this case, we're going to be better. We're going to say that there's something behind us, some system that's running us that allows us to make these non-deterministic choices, and if the choice fails, it says, okay, that's fine. There are other possible choices that could have been made. So it's sort of a backtracking framework that this whole thing is engaged in. So here's a programming language that strongly resembles something we've done before. And suppose that we want to parse that string, ID times ID end of file. And you'll notice that this is a left recursive grammar, so it means if I were to just write this as recursive descent, it would blow up. But let's look at what happens here. So I could have a failing path through this. I could, as my first production, I choose P goes to E end of file. So the first step in parsing that would be to parse the first step with an E. So we start trying to find an E in that string of characters, ID star ID and so forth. And let's suppose that the first thing we do is we choose ID. So we choose the first production. So we choose to match E with this rule here. Now that's going to fail because it doesn't take into account that trailing star ID, but we'll try it. So we try it, and eventually what happens is that we come down to here. We check that the first symbol is ID. It is. So we increment K. We go to the next symbol of input, and we say, and we're done. We return 1. So we're done. We've 1, meaning we have consumed 1 character of input. We come back to here, and eventually we say we'll check we come back basically to this level right here. We found ourselves an E that matches T, and now we try to match symbol 2 against end of file, and that fails because the second symbol is star. So that's a failing path. That path does not work. We give up, and this so that's not how we're going to parse this. But on the other hand, if we make the right choices, we'll get all the way through. So we choose. We have to choose. We only have 1 production to choose in the first case. So we choose the same thing there. But for the second case, let's suppose that we choose to parse E star T instead of T. So we choose the second production. The fourth production, this one down here. Well, if we do that, and if then when we come down and start parsing that first E, if we then choose to take T goes to ID E goes to T as our choice, everything's fine. You'll see that it actually works in that case. We come through, we parse the T, that's fine. It returns the position that we've consumed. We check that we have a star second. Yes, that's fine. So we keep going. We check that we then check to see whether we have a T after that, and assuming that we do, we have. It turns out that matches ID perfectly, so everything's fine. And so we will have consumed the first 3 characters, ID star ID, or through first 3 tokens. And at that point, yes, we come back to here. We come back to the P, E followed by end of file. And yes, we do have an end of file now, so it succeeds. So this is a path through the parser that succeeds. So if we only had some kind of system that allowed us to that handled these blue things properly, in other words, allowed us to make a choice and succeed or fail, and if we fail, we have another choice that we can make. If we had something that did that, then we could actually parse anything. We could parse any context-free grammar. There is one other caveat. It's actually not quite as simple as that because, of course, you still have to avoid the infinite recursion. So somehow this system has to find a path, even though some of the paths might be infinitely long before they fail. But it's just a matter of choosing the right thing. So this program, and you'll probably have to meditate on it a while to see exactly what I'm doing here. But this program here captures general context-free parsing. It's just that it calls for us to do it calls for us to accomplish a miracle here on the blue line. And the question is, how could we do that? How can we possibly do this non-deterministic thing and keep track of everything? So one way would be, of course, to have an infinite supply of processors. You've heard of multi-core, and around here we talk about many-core. Well, how about Cantor core, an infinite number, or mega core, or something like that. An infinite number of processors. Well, then it's easy. We just spawn new. Every time we come to one of those non-deterministic choices, we just spawn a new process and have it carry on from there. One for each production, for each possible non-deterministic choice. Now, some of these would give up, obviously. Some of them would loop. The ones that that consistently chose the left recursive branch, they would loop forever, right? But there's an infinite supply, so let them loop. Yeah. We'll make more, and some of them might succeed. And if you were trying to be efficient about your use of your infinite supply of processors, you might have some little communication mechanism so that when one of them succeeds, it stops all the others. I don't know. Since, we can contemplate that, but since, of course, there is no such thing as infinite supplies of hardware. Indeed, just a couple of weeks ago at our weekly faculty Friday relaxation, big ideas meeting, as it's called, where we just sit around and drink sherry and talk about stuff. One of my colleagues was telling about, Professor Yablonovitz was telling about the theoretical limits on how much computation can be done in the universe based on quantum mechanics and cosmology and so forth. And it's much less than infinity, unfortunately. So we can't do that. We'll have to come up with something deterministic. We'll have to come up with something that you can do on a few processors or even one processor. So that means that we somehow have to keep track, instead of having a lot of processors, each one of which keeping track of its own state. We have to have some way of keeping track of this state ourselves. And this line of thinking led to what's called Early's algorithm. It's called Early's algorithm because it was invented by somebody named J. Early, who was a Berkeley PhD student some years ago. And now apparently is some sort of psychologist somewhere. It's very interesting. There are all of the computer scientists that start restaurants or take up yoga or something like that. It's an interesting group of computer scientists, and many of them have famous names that attached to algorithms, and then they disappeared. Okay, so this is an algorithm. We're going to see an algorithm that handles any context-free grammar. It finds all the parses of any possible string, of any string. So if it's ambiguous, it works fine. And it's really very nice. It will recognize a string as being a member of a grammar in n cubed time if the grammar is ambiguous, in n squared time if the grammar is non-deterministic. This is a technical term. It basically means if the grammar would not be parsed with with our tools, right? If it's unambiguous but could not be parsed with our tools, then there's an n squared bound on it. And if it could be parsed by our tools, then it's a linear algorithm. So this is pretty good. It's a pretty nice little algorithm. And we'll turn to that next, but I think at this point it probably would be a good idea to take a break. So questions, first of all. Yes? N is the length of the string, and the string that you're parsing. And the constant of proportionality here depends on the size of the grammar. I saw another hand. No? Okay. Same question, right. Okay. So I'm glad that you're asking that question. We spend a certain amount of time getting people to ask that question because it is kind of it is kind of important. You know, you'll have an algorithm where there are 7 different variables, and they'll say that you'll say that it's O of n, and we have no idea what that means. So good. I'm glad you asked that question. That was a good question. Fine, good. Let's take a break.
Algorithms class, I'm taking it at the same time.
Yeah.
They said that the best factoring algorithm was O of 2 to the something, and I was like, oh, what the heck? That takes forever. I can do better than that. And I figured out, oh yeah, I can do it like n to the 4. Basically.
It's the number of digits.
Right.
Yeah.
Right. So actually, it was 2 to the 4n. You know, not.
But it's what you were thinking of as 2 to the log n.
Right. Yeah. So anyway, yeah, it was just super horrible algorithm, but yeah, it depends on what the n is.
Yeah, that's right. It's very tricky when it's very tricky. All of those problems where you're dealing with numbers, but from the algorithm's point of view, it's really the number is actually the string that represents the numbers.
Other thing about you said you have Yvonne's
Yeah.
professor? Yeah, but I've been told I should go talk to him at some point by a different professor. But the whole thing about quantum mechanical limits on computation, I'm still holding out hope that some of quantum mechanics may be
wrong.
Well,
nonlinear. Yeah.
I don't think it's wrong. I think it's in the same position that classical was 100 years ago. It's a very good approximation to the truth. And in a statistical amount of time, like if you take a long amount of time and you make a statistical observation on what happens, and yeah, it works out. But
well, the interesting thing is that the mathematics of quantum mechanics says that it's deterministic, and the probabilities only come in when you're trying to interpret it.
Right. Yeah.
So in other words, when you're trying to get numbers out of it, because you possibly can't know all the information you need to know to get any exact computation. But
what I'm concerned about is I think that the way that they're teaching quantum and physics in general is actually pretty much completely bringing to a grinding halt any possibility of progress in the field, because like when I was taking it, especially like 7 and 8 series, they were just hammering into us that that this is not deterministic. This is exactly how it happens. They've proven it. It's been 100%. It's for sure. You can't even question it. If you question it, it means you're crazy or stupid or wacko. And then it makes people not want to really think about things.
Well, there's a story that I forget. I think it was Stephen Weisberg, I guess, told about talking to one of his colleagues and asking, well, what's happened to so-and-so? And he said, oh, well, he's trying to understand quantum mechanics. He's trying to interpret quantum mechanics. And they sort of, had a mutual sigh, because basically the way to actually do any work in physics is you sort of have to shut up and compute, because that's just the state of our knowledge.
Yeah, although, I don't know, I've been spending some time trying to, the research I want to do actually has to do with like computational chemistry and making better algorithms for that, and with better physics. Like, I didn't come into this thinking I'm going to question any physical junk. I just wanted to use their equations, right? And then I started reading the history of where they got these equations and the personalities involved, and it's ridiculous. Like, I feel like they've been stuck in a rut for the last 10 years.
Yep. Well, yes, and it makes me shudder to think that when I was born, it was a raging debate.
Really?
And then, I mean, the 50s?
Well, and that's
sure.
the thing. I do not anymore read any books on physics written past 1960-ish, because they stop even footnoting stuff. Like, basically, the books from the 50s are actually the better of the graduate quantum mechanics books. They actually footnote it still. They'll actually say, well, there are no hidden variables theories that work, but, oh wait, there's a footnote, except for there's a few that maybe have not been proven.
You should be. Have you read Bell's? Bell's book?
Yeah.
He's a remarkably clear writer, I find.
And yet they twisted it around, and they said that he supports that anyway.
Yeah. It's strange. Okay. All right. Okay, so let's look at this algorithm. And it's not as if this algorithm is widely used or anything, unless you actually have to do this parsing of a large number of sentences. But out of this comes some ideas that we can use for a more practical algorithm that we actually can use for doing parsing. So here's what we're going to do. First of all, I'm going to transmogrify the algorithm just a bit, so that I have enough explicit state to grab onto, so that I can. Then I'm going to put in a data structure that keeps track of that state. So that the state, by state I mean what would normally be the state of a processor. We're going to capture in the data structure, so that we can write a routine that basically keeps track of what all of these infinite supply of processors would do if we had them. So the basic algorithm I want is one where I'm going to give you as the argument, I'm going to give you a production, A goes to alpha B, except that I'm going to mark a point in the middle of that production with the traditional symbol is a dot. I've drawn a very big dot because the traditional symbol is actually a period, which you often can't see from the back of the room. So I'm using a really big dot. And what we're going to do is the assumptions when you call this function is that you have already found the alpha part. In other words, you've matched the alpha part to part of the string. Everything you've already matched it to everything in the string up to position k. So everything from so basically we're starting we start the string in the middle at position s. Position s plus 1. And oh, by the way, we're assuming in order not to pass the string itself around all the time, we're just going to assume it's a constant through all of this and just call it capital S. It has characters C1 through Cn. That's the input. And we're at each stage here that's going to be a global variable, and this function is going to look at them. So I'm going to call this function, I'm going to say I'm at position S in this string. I've parsed everything up to position S. So let's look at the rest of the string, and let's assume that we've already parsed everything from position S up to position K, and that matches alpha. And what I want you to do is figure out whether you can continue parsing from this point so as to match beta to the string after K. So that's the idea. I should probably put a diagram in here to show this diagrammatically, but I'm just going to talk it through for the moment. And so I want to write a recursive program to do that. Okay, well that's fine. Now I admit this is terrible. There's no motivation for why I have chosen these particular arguments, but we'll sort of see how it works in a bit. So how do we do this? Well, obviously, if beta is empty, if there aren't any symbols after the dot, then we've succeeded. We found it because by the assumptions of that function, we have matched beta to the empty string, which you can always do, and everything's fine. So we'll just say, okay, yes, I've done it, thank you, and I'll return k, indicating that we have matched everything up through. We have now matched everything up through c sub k. We've matched all the string up through c sub k. Otherwise, beta has some symbols in it. Let's call the first one x and call the rest of them delta. I just love these Greek letters. Okay, so symbol x, if it's a term, we do what we did in the last symbol. If symbol x is a terminal symbol, then we will we've successfully matched symbol x, and now the problem is to match the rest of beta, to match the trailing part of beta, which is this string delta. So we'll just recursively call the parse procedure, and we'll say now we have parsed everything up through x, and we want you to handle delta. That is, we ask you now to try to match delta to the rest of the string. starting at position k plus 1, because so we've matched everything up to position S matches we've already matched everything up to position S. Everything between position S and position k plus 1 we've matched against alpha x, and now we'd like you to now try to match delta against the rest. And if on the other hand the terminal symbol x is a terminal symbol and it doesn't match, then we give up. Right? So this is actually the same algorithm as before. I'm just breaking out a little more. And then finally, if if the next thing that we have to match is a non-terminal symbol, well then we do this non-deterministic thing. We choose a production non-deterministically, and we try to, and starting at the current position, we try to parse that non-terminal symbol. We try to parse that production. We try to use that production. So, and then if assuming that succeeds, assuming that non-deterministic thing succeeds, we then continue parsing, just as we did for the non-terminal, except we parse everything after the x, and after the part that the x is matched. So we parse everything after the part that the x is matched. So we do this. So this is now, I've just made the previous algorithm as if that wasn't complicated enough. I've made it more complicated by throwing in this extra stuff. But by so doing, I've now made it possible to use a technique from 61A called memoization, except we're going to do memoization on a grand scale. So this chart here, what it's called, it's traditionally called a chart when you talk about these algorithms. These are called chart parsing algorithms. This corresponds to our memoization set, and the arguments. And it turns out that these arguments here, so given that the string S is fixed, these arguments here are everything you need to keep around in this for doing this memorization thing. So in particular, this is actually going to save us from the infinite loops, because we will see that we have already done. We will see that we're doing something that's already been attempted. So for each one of the argument triples, we will put an entry into the chart, keeping track of what the answer is. And we'll just, rather than do an ordinary memorization table, we traditionally organize this into a table with one column for every value of k, and group the other two things into that column as what's called an item. So we'll keep track of a bunch of items that have this appearance. And what this item here means is that we've parsed everything in the string up to position S, and we've parsed, and then everything between S and the current column has been parsed by alpha, and we are now looking at beta. So here's what it looks like very briefly, and we'll finish this up next time. This is an example of all of the stuff that you keep track of when parsing that very simple grammar that you see up there. That very simple ambiguous grammar that you see up there. So we'll see. You can look at this please before Friday, and we'll see how this rather mysterious looking chart is actually giving us all of the parses of that string. And then, just so you can see what's coming, we will extract some ideas from this algorithm that can be used to build a useful tool for parsing a subset of these grammars. All right.